So, hello everybody. Welcome to PLC2's webinar VHDL Circuit Design Part 1. My name is Eugen Krassin. I'm your presenter today. Now let's start actually with our VHDL Circuit Design Part 1. Okay, so the second part will take place in, well, later on, I think next month. Well, that's is the overview. The agenda actually, so first overview, some information about designing FPGAs, the VHDL concept itself, designing with VHDL, VHDL operators, modeling behavior, and so on. So that would be the full stuff here, but this is actually divided in two parts. So this will be the agenda for both, actually, for both parts, because it would be too much information for just 1 hour. So I divided this in two parts. So first, let's start with the overview. Well, you see, first, for somebody who don't know what is an FPGA, just give you some very basic information here. So you see that would be a gate array. This means for the gate array, we do a prefabricated, maybe gates, like Boolean gates, whatever, and then maybe that could be PAL, or it could be a gate array. Let's assume if this is a PAL, the former technology, then we do have some fuses. Here we go. And during the program we basically burn the fuses away, and then we got the resulting structure. So, but this is very old. That's actually we're not using this anymore. Today we're using FPGAs, and that's actually the idea. FPGA is a matrix of such blocks. Such a block is called a CLB. A CLB stands for configurable logic block, and this is a matrix. Could be thousands of such CLBs, could be actually arranged in a matrix, 20,000, 30,000, 40,000, and so on. And this matrix actually is surrounded by peripheral cells. So these are IOs. Here we go, IOs. So this could be an input, that could be an output, or could be bidirectional input and output, something like this. So this means bidirectional or tri-state. And again, depending on the package you select, could be thousands of peripheral pins connected to the internal matrix. And then, that is very important, we do have a lot of routing channels. So these are already predefined, pre-built routing channels. They're already there. So this means during your design of the FPGA, you never make connection in terms of build some routing channel, or you just destroy some routing channel. No, these routing channels are basically multiplexer structures. This means by programming a multiplexer, you can actually select, let me actually maybe show zoom in here. So it could be a so-called switch matrix here. It would be here, for example. This switch matrix might have maybe some channels horizontal, vertically, and then you can actually, for example, you decide to use this routing line here, and you would like to switch maybe to this one, then you actually select the multiplexer and you just switch from this line to this line. So these are switches, but these switches, you're not really building the switches, they're already built. You're just selecting the switches. This means in order to make this FPGA work, we need to program this with a bit file. Okay? So if you just enter bit file and you load a bit file here, a single bit position, for example, here will define the position of this multiplexer to be this way. So this means depending on the complexity of this FPGA, we have maybe a bit file, maybe few hundred kilobits up to megabits of data, which must be configured during the time point 0. And then if you switch off your FPGA, then again it's empty, and you can reload a new a new design. So that's actually, I'm pretty sure most of you know already the structure and the principle of FPGA, and that's what we're going to talk about. This means this is maybe a little bit more, at least colored picture of such FPGA. You see, so these are the CLBs. So these CLBs contains the logic we will actually configure, like gates, like flip-flops, whatever. Then we do have RAMs. In order to, these block RAMs are here in order to support, memory structures. I need a lot of RAMs, for example. Then I would use this embedded block RAMs. Then for a special application for digital signal process, we do have some special DSP IPs, which are also available here. And again, this is surrounded by peripheral cells. Some of them are general purpose, IOB, but some of them are maybe they have a special use cases, maybe serial high-speed TX or transmit receive, for example. Also, in order to support the interfacing to DDR external memories, we do have a memory controller usually, which is also implemented inside FPGA. And in order to support the generation and modification of internal clocks, we do have actually usually a lot of PLLs available. And these PLLs are here in order to actually generate, maybe using an external oscillator, maybe with, I don't know, maybe 50 megahertz, but we need internally maybe 5 different clocks with different frequency, maybe with a different phase relationship to each other. So we can use these special elements in order to generate our frequency. So these are the basic elements of the FPGA. But again, in a different webinar, I'm talking actually about the architecture itself, so we can spend actually more time talking about architecture. But during this webinar, this is just introduction to you, just maybe a review of FPGA, because we will concentrate now on VHDL. How can I use VHDL in order to configure and program such units like CLB or RAM or whatever? Okay, this means maybe just because we will going to talk a lot about this, let's look maybe inside the CLB. What is inside the CLB? Because we will have now, we need to deal a lot with such CLBs. So if you look inside the CLB, then you see that's actually what happens. So this is CLB. And inside CLB, we do have 2 slices. You see slice 1, maybe, that might be slice 2. And these 2 slices are identical. And if you look to the contents, what is inside such a slice, we do have a unit called LUT, lookup table, and we do have 2 sequential elements. So what is sequential element? It's a flip-flop or latch. These are the sequential elements, and there are 4 of them. Okay, so this means what we're actually doing. These are the basic elements. All our FPGA designs, all of them, there are no exception, all of them maybe maybe constructed, and they are constructed using such structures. We always have some gates, whatever it is, some gates connected to a register. Again, maybe some other gates connected to a register. This is the general structure of all, no exception, of all FPGAs. And you see, this is actually the location where this structure are generated inside the slices. This means now we need to understand how can I make a description of my design, and how this description actually is placed inside the lookup table. This means the lookup table is actually the location where the gates are realized, implemented, combinatorial functions. And the sequential elements are the elements where the flip-flops or latches are realized. That's the point. Okay. We will also learn that this lookup table, it's a very, let me erase this one here. This lookup table is a very flexible device. This means this lookup table, and I will show it actually to you. This lookup table may be used, as I already mentioned, to implement gates, okay? Different kind of gates, but also may be used to implement RAM, a small RAM. In this case, if you implement the RAM, this RAM would have the complexity 64 addresses, 1 bit wide. But as an option could also be 32 addresses and 2 bit wide. But the total RAM bits per lookup table would be 64. And the third use case for such a lookup table would be a shift register. Yeah, a shift register. You can implement a shift register, shifting data in and shifting data out. Okay. So depending on your description, depending what you are typing, depending on VHDL code, okay, this different description will be placed in such a lookup table. So that's actually the general structure here. This means if I look a little bit more closer in such a slice, just to give you an idea, that's how it looks like. So again, this is the lookup table, which is responsible for implementing, you see here, lookup tables or RAMs or shift register. And these are actually the 2 sequential elements per lookup table. We do have 4 of them. Okay. And there are, I will explain it a little bit later. There are some special logic elements which are built in. For example, this one and this one. You actually, if you look a little bit closer, you will actually see this is some kind of a path here. Okay. So entering the slice and leaving the slice. So in this case, it would be the carry logic. Okay. This means whenever we need a carry generation, that's usually carry is usually involved in sum is equal to A plus B, then a carry is involved here, or to A minus B. That's also a borrow, which is also some kind of carry is involved here. So this means whenever we describe something like this, then the synthesis tool is clever enough to place and to implement this carry generation structure inside this very special structure inside the slices. So this helps very much in order to reduce the overall complexity of the FPGA. Okay. And then finally, the input-output cells. So this means, so these are, again, if I give an overview, this is the matrix, So these are all the CLPs here. Here we go. So then these are the peripheral cells, which are maybe somewhere like here. And this peripheral cell here is this. Yeah, is this one. So this is just that. This is actually, so this maybe it's too much. So this is actually this cell. Okay. So this is actually the fabric. Fabric is, the name fabric implies that internally. So, but this is a cell. So this is the pin actually. Then we do have an input, we do have an output, depending on whatever you select in your description. This could be an input. So if this is an input, then this will be disabled, okay? Or if this is an output, then this will not be used, but this will be maybe enabled, okay? And then just some information. We do have also some kind of complexity inside every cell. We have some very special logic which allows us, maybe if there's an input, to delay an incoming signal. So I have an input, but maybe for some reason I would like to delay it maybe by, I don't know, by 100 picoseconds in order to fine tune high-speed data transmission, whatever. I can do this, or I would like maybe to register this inside the cell, not just running with a high-speed net, maybe internally, just do the registering inside the cell. then you can use flip-flops here. Or if you like for high-speed application, you would like to have a serial parallel for the input. Serial data input, but you like to have a serial parallel conversion right here in the peripheral cell. You can use this. So this means you have very, very special elements inside the IOBs called input-output logic and I SERDES and O SERDES, including delay. Again, more in my webinar when I talk about the architecture, then I will explain in more detail. Okay, this is just an overview to get familiar with the technology here. Okay, now let's talk about designing FPGAs. So this means, what was the traditional method? Well, this was the traditional method. That's what I started. My job was designing ASICs, in the 80s. So that's what I started. This means whenever we designed the ASIC, so then I used the schematic capture tool, and then this was a 4-bit synchronous counter. This means this case I need to understand, I need to learn how should I design a 4-bit synchronous counter. So this case I have to place a flip-flop here, and then you see I have to design this feedback. This is a toggle flip-flop which toggles all the time, or here this is a toggle flip-flop. Only if there's a carry here, then it starts toggle. So I need to understand this, okay, how to do this. And I actually start drawing this, and that's what actually was built, okay. And then these elements were sometimes already available in the gate array. They were placed and routed. So that was the job. Very, 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 very time consuming and very, very error prone. And this means the complexity is limited. This means this kind of design, I think if you design, well, what was the complexity usually I did, it was maybe 15,000 gates. Okay, so 15,000 gates, and that's approximately was the limit. You couldn't do more because it would take you 1 year to do this. But today we decided 2 million, or maybe 3 million gates. So you see, that's a big difference. So we're not doing this anymore. Okay. So what you do now, we're using VHDL in order to do actually the same design. But again, using VHDL, we do have 2 methods. So this is method 1. It's not, I tell you, it's not very good, but you can do it. Okay, you can do something like this. You need to describe a counter. You know this. So now, then it's called a structural. Yeah, you first describe an entity. Entity means this is how it looks like from the external world. Entity, you say there's a clock input. Here we go, and for output, Q0, Q1, Q2, Q3. It's a vector CQ 0 to 3. So this entity, you will learn this. This is just how this look like. Okay, and now during the architecture is internal. Now you can say it's not good, but just to make to show you the difference. Then you can actually take a component conf inf. Here we go, inverter, and connect pin A to and pin B somehow. Connect the pin A to a net called S1 and connect the B to a net called S2. Then you replace the next component called DFF, so that could be DFF. And then connect again, maybe the input D to S2 and so on and so on. So you write some kind of a net list. You can do this, but this is not, VHDL will allow you to do this, but this is not what we do. We use sometimes this kind of description in order to build hierarchical design. This means U1 and maybe U2, but it's a hierarchical blocks. They are connected somehow together. Okay. Then we will use this methodology, but we will never use this methodology in describe, this circuit using simple components. Now that's not the case. We will do something different. Instead of doing structural, we are doing behavior. So we just describe the behavior, not the structure. We are not defining that this gate is connected to this gate. No, we don't care. We just say, okay, the box looks like this from the outside view. The clock comes in and the Q comes out. So we just describe a black box. Something comes in, something comes out. We are not interested in the internal. But now we just describe the behavior. We say, okay, what happened? Okay, when there's a rising edge, it's a function with a rising edge of the clock. So this means when there's a rising edge here, this is a rising edge of the clock. If this happens, then is the new value Qi. Qi is internal. Qi is a Qi. Qi is incremented, and because the outputs are Q, we just move the Qi, connect the Qi to Q. This is just a connection from the internal signal to external signal. So you see, so in this case, you don't care how this will implement. You just say, okay, if there's a rising edge, just add one, or we can also say or decrement. And this is called the behavior. So this is how we do. We don't care about the internal structure. We just say, if this happens, do this. Okay, that's actually the hardware description methodology, and this is what we are used. So now, in order to understand and to start working, we need now to understand the principle. What is the entity? What is the architecture? And what are the commands? And now we need to learn how to use this. Okay. So now this means let's look at our FPGA design flow. This means first we have to describe it. It's called design entry. In using HDL, this would be VHDL, or Verilog. This would just a different hardware description language, but we are talking about HDL today. We describe this. Now the synthesis tool understands your description and translates this to a netlist. This is a netlist, and this netlist is finally implemented in a lookup table and flip-flops, and layout is generated. And then, and what you can do, this is a very, very nice option, of course. It's also a webinar, which I will do, I think, in July. Before actually we go to the synthesis, we would like to understand, is it correct what I'm doing? Is it really correct? Then we will run a simulation, a function simulation, just the function, no performance, no timing, because this is just theoretical. This is just source code, okay? So there's no, the function is there, but not the timing, for example. But once I implemented this, I can go back. And now, when I go back, then all of the layout information, all of delay information from the layout is extracted. And now when I perform the simulation, I see the function as well as the timing performance. Okay? And I can also do a theoretical analysis by timing, or I can actually do timing simulation in order to understand my performance and did I, met the requirements I have. So that's a general design flow, and we are going to talk about today about this. How can I do the description here, and what are the rules? So first, what happens? What is the synthesis? We'll go back. What is the synthesis about? What's all about? Well, let's assume we would like to do this. Yes. Well, yeah, this should be implemented in your FPGA. So now, what could be easy? You just describe a Boolean function, or a Boolean equation for the output y based on inputs A, B, C, and D. For example, something like this: y is, so this is assigned. This symbol is assigned to. So y is assigned to what? Now A and B. So this is AND gate, or C. Okay. This is this one, and XOR D. So this would be the XOR. So now we use the Boolean equation and or maybe an XOR, but you can also use NAND and NOR and XNOR and all this stuff. So you can do this. So very simple and very fast. Now, when you hit the button and say, I would like to implement this, then the synthesis will actually analyze this structure and say, okay, I do understand this is the function, and then this equation is actually first translated to a lookup table, because it's a lookup table. So in this case, you know what the synthesis will do. So I do have the, maybe the 4 inputs here, and this would be the output Y. So this is A and B and C and D. Because of 4 inputs, there are 16 possible, values here, 16 possible situation, and then the Y is calculated 0, 1, 0. So this lookup table is actually implemented right here. So this lookup table is nothing else. Therefore, the name lookup table, it's a truth table. So this means the combinatorial logic is always transferred to a truth table first, and the truth table is implemented in this lookup table here. And you remember, I told you the lookup table may also be used as a RAM. Yeah, and that's because the RAM is really the silicon. What is behind the lookup table? Because lookup table is a RAM, because these are the addresses, inputs are the addresses, and the output is the contents of the truth table. Okay, and during time point 0, during initialization, this lookup table, which is synthesized, will be loaded inside the lookup table. That's it. That's how we program the FPGA. So this means if you run the synthesis, that's actually what we get inside the FPGA, you see. Then these are the inputs. These are the input level shifter. Because, internally, FPGA internal operation could be 1.8 volts, and the inputs here could have the standard maybe 3.3 volts. So this is the level shifter here. So this is the input block, input blocks here. This is internally the FPGA, is a lookup table, and this is basically the output block, which again transfers maybe to a level of 3.3 volt. Okay, so this is actually what happened during the synthesis. So, and you see that again, I described this. I would like to describe this. Now, that's what I'm typing inside my my VHDL, and say that, and then hit the button synthesis, and the synthesis will actually do this structure, and this lookup table will be implemented, for example, here. And this input will be implemented somewhere here. So these are the IOs, okay, and they will be connected somehow here, okay. And this output will be connected maybe here, and then it will be used output here. That's actually how it works and what happens inside the synthesis. Okay. So, but what happened if you? So this is pure combinatorial stuff. Okay. But what happens if you like to have a registered logic? This means you have here the combinatorial stuff, yeah. But then, yeah, maybe you would like to connect a flip-flop, which is using the clock. So now, how can you do this? Simply write a condition that I would like to output this signal here, this one, but only, so this is this, but only when, so this is the condition, but only when what's a rising edge. If there's no rising edge, don't do it. If there's a rising edge, then transfer it. So this means whenever you ask for a rising edge, you will get a flip-flop. If you don't ask for a rising edge, you will get a combinatorial circuit. So that's the methodology how can we actually describe them. The registered function. This means now, if I do this, and I basically describe this, and I run the synthesis, I will actually get again this logic. So again, this lookup table, which represents this block, will be implemented here because it's combinatorial. But this flip-flop, which is here, which is described here because of the condition rising edge, so this flip-flop will be implemented here because here we go. And because inside the slice, there's a connection from the loop to the flip-flop, maybe this one here. this connection is this connection here. It will be used, and this would be the output. You see, this is how it works. We just understand the methodology, how to describe it, and then the synthesis will translate your description to the architecture and to the logic here. 1 second here, and actually to the logic here. Okay. So this means, oops. Now, so it was just an overview. That's what really happens. Now, the concept. What is the concept of VHDL? So now you need to understand VHDL was invented not for synthesis. It sounds strange, but that's true. The VHDL was not invented for synthesis, not at all. VHDL was only invented for simulation, not for synthesis, for simulation. Simulation was the initial idea of VHDL. And so VHDL was used actually to describe hardware and to simulate the behavior of the hardware. Synthesis was not born, okay. But later, maybe years later, you know, clever people they said, oh, maybe I can invent a tool which will actually synthesize my description to real hardware fully automatically. And then this was implemented, but the original standard which was developed was not changed. So, and now the strange situation, yellow. This is simulation. Okay? So these are all the constructs available in this yellow area. Yeah, can be used in simulation. All of them. No exception. All of them can be used for simulation because it was developed for simulation. But only one part, only one subset of all the statements which are in this yellow area, only a subset may be used for synthesis. Only a subset. This means now you need to learn two different kinds of how to use VHDL. You need to learn some constructs are synthesizable, but some are not. But all of them may be used during simulation. So we need to understand this, and you will learn also that which constructs are synthesizable and which constructs are not synthesizable. Okay, so that's the idea. So this means VHDL is a model language, not a synthesis language. Okay, so this means all VHDL can be simulated, but only few constructs are really may really be used for synthesis. Okay, for example, a very powerful construct here is do something, now wait. So wait, will I wait for 5 nanoseconds? Okay, very powerful. We can use this several times. Very powerful construct. But it's not synthesizable. There is no hardware which is available which waits for 5 nanoseconds. It's not possible. But of course, it's very nice to model something for simulation. I can say now wait 5 nanoseconds, then do something else. That's okay. But you cannot synthesize this statement because no hardware is available in our real world which waits for 5 nanoseconds. If you would like to wait for some time, then you have to design a counter. And you have to load the counter, you have to decrement or increment the counter for a few cycles. And then if the counter expires, this gives you the time. But this is different. You have to design a circuit. But there's no way for you to wait. Okay. So this means, again, just to make the difference, if you would like to describe something like this, there's one bad way available. You could use primitive components and connect it somehow. You have to name the nets and connect it somehow. It's not recommended because it doesn't make sense. It's not behavioral. So use behavior description actually that's what we need to do. Okay, behavior description is our choice. Okay, so but now very important for us, very important. That's VHDL is a very strict language, very strict. Okay, and therefore we do have a very strict type concept, very strict type concept. This means VHDL is a very strongly typed language. Before you can actually say, I don't know, maybe let's do a counter. Sum might be sum, or yeah, sum just adder, or A plus B, for example. Okay, so if you would like to type this statement just to describe a counter, so this means your idea would be in this case to do this. Okay, maybe n bit wide here, n bit wide here. So this would be A, this would be B, and you would like to add it and to get a sum here. Okay, so if you do this, you have to make sure that the signals A, B, and sum, they must be of the same type. They must be of the same type. This means before you can use actually the signals in your description, you have to define the signal to be of type A or of type X, the signal B of the same type X, and the signal sum of the same type X, and then you can use it. If the signals don't have the same type, you will get an error message. Okay, so that's actually very important for us. And in VHDL, inside VHDL, we do have actually, let's say, 4 major types which we can use. Let's say, not major, more types. Let's say 4 major groups we can use for our description. First is the scalar group. So this means in this group can use types, numeric, enumeration, physical objects. So these are scalar. We can use composite, the composites. So we can define arrays and records. We will learn this. What this is. Access. This is, let's say, a pointer. We can define pointer. It's called access in VHDL, or file. But this is, of course, not for synthesis. This is used for during simulation. We can, read and write files in order to, store maybe log files or get some stimuli file. So very important. We have to understand the VHDL type concept. Otherwise, it will not work. Okay, and these are actually the predefined types we can use immediately when we start our project. So, and why? Because VHDL has the concept so-called packages. A package is a container which contains definition. There's one package available as a default, it's already there. It's called standard, and this package standard contains all the predefined types we can use immediately. For example, we can say we have an object signal A, which is of type Boolean, for example. Okay, so and the type Boolean means since the value the signal A may have, the value is, well, it's true or it's false. That's the value, true or false. If you define, for example, signal B of type bit, then the value is 0 or 1. If you define a signal C of type integer, then it's actually minus 2 to the power 31 plus 2 to the power 31. I think this is minus 1. Or this is okay. This is minus plus 1 here. So see, there's a number. Okay, and so this means you can use it immediately without any other preparation. You can also use the type time. So if you find t of type time, then the value would be an integer 7, or could be also real, would be a floating point 7.2. And now the physical unit, because time needs a physical unit. Unit would be time value, for example, nanoseconds. Okay, so this means whenever you use connections, so-called signals, you have to define first the type of this connection of the signal, and then you can use it. Okay, and you see some of the types are synthesizable, some not. So these are all synthesizable. So for example, real is not synthesizable. Not immediately. You cannot define a signal R to be of type real and say I don't know 5.5.7. No, it's for a simulation. Yes, it's nice, but it's not synthesizable. If you would like to deal with real number, you have to define maybe your own package, and you maybe have to use an IP core which actually transfer and generates the real number. So it's not synthesizable. Also, string, which is a string of characters, not synthesizable. It could be in some sometimes it is synthesized. It depends a little bit on the tool. Bit vector, it's a vector of bits is synthesizable. Time is of course not synthesizable. We cannot synthesize the time. So you see, we need to understand some are synthesizable, some are not synthesizable. So this means, and that's the idea. How do we deal? So now we know this is VHDL. This is the VHDL standard. Okay, so that's our work. This is our FPGA, what we define. Because we define the FPGA, we would like to synthesize the FPGA. So we have to use all construct out of the synthesizable region, because we need to synthesize the circuit. But now we need, of course, to run the simulation. So we need maybe to describe a oscillator, or maybe to describe a reset generator which resets, or maybe I would like to observe the signal by having, maybe a model which receiving the stuff. So the environment, but this environment, I will never synthesize this environment, never. This is just for checking the function of my FPGA. So in this case, I can use whatever I like. I will never synthesize this. I will only synthesize this. So this is your job, to understand which is synthesizable and what is not synthesizable. Yeah. So for example, just to show you a typical situation, what is synthesizable, what is not synthesizable, and maybe why is this maybe important for us? Okay. For example, a customer calls me and asking me to do the FPGA with some function. And what he's telling me is that he tells me, well, I would like to do something like this. Maybe he's not an FPGA expert, the customer, but he can draw a time diagram. For example, he can tell me, okay, the box here, what I should do, should behave like this. If there's an input signal, maybe a pulse here, okay, then what should happen? Then the output signal, after a time, the output signal must go immediately also to a 1, immediately, but only for a duration of 10 microseconds. Then it should go down, deassert again, and wait for the next event. So if the next pulse is there, just repeat and do the same. So he's telling me he would like to have this function inside the FPGA. What I can do, just in order to make sure I understood correctly, I just can immediately describe this in VHDL. And we will learn this. I say, okay, first I describe an entity. This entity tells entity, the name is behalf. I is an input, yes. O is an output, yes. And the entity is just a box. View from the outside world. It's just a box. And now the description. I say, description is, first, O is 0. O is 0. Okay, here we go. O is 0. Then, wait until I becomes 1. Well, so wait until I becomes 1. This means wait for the change from 0 to 1. It's exactly this point. It's exactly this point. Then if that doesn't happen, the wait shall stays here and waits and waits. It's a wait function. No, it happens. Now just place output O to 1. Okay, output O goes immediately to 1. Here we go. And now wait for 10 microseconds. Now I wait for 10 microseconds. Here we go. And then end process, and process. You know what this means? End process is always go back to a process. And the process itself is always an endless loop. Process is always endless loop. So this means this process runs in a loop, endless, because it's also endless. So this means I can do this in few minutes. And then what is the big advantage? I can actually run the simulations. Immediately I can run the simulation. And what I will see exactly this behavior. And then I can go to customer and say, is this the behavior you would like to have? Is this a behavior? And you say yes or no, maybe, whatever. And then I can do it. And this was initially the idea of VHDL. Run the simulation. Make sure you understand the function. Make sure the function, the intended function is there, is correct. Then you can design the hardware. So I can do this exactly, but I cannot. Unfortunately, I cannot use this description inside the synthesis, because the synthesis will tell me no, I cannot do this. I cannot implement the weight function. I cannot implement the time function. Oh, sorry, that's impossible. I can run the simulation, but I cannot run the synthesis. So I need to find a solution. How can I do this really synthesizable? But I know this is the function I would like to implement. So this is already very, very important. So the question is, how could I implement this function? Well, in this case, I would do something like this. So first, because I cannot wait, I need to understand, okay, but in order to wait, maybe some time. So if I go back here, you see in this case, there's a wait time involved, 10 microseconds. So in order to wait for something, I need a clock. So therefore I would need a clock to the real hardware. Okay, maybe I would decide to use a clock of 1 megahertz, because the duty cycle period would be 1 microsecond. So I can have maybe a counter, it counts to 10 or something like this. Okay, so and what would be the internal operation? Well, there's a lot of different solutions possible, but maybe the best solution I would do this. I would have the pulse which comes in, here, set immediately the output, yes, and then it is a shift register. Let's say this is a shift register. And now the one, because it's a pulse, it's just stored here, and then the one is moved with a clock. With every clock, the one is moved, because 0 now is output, the one is moved. Okay. If you have here 10 flip-flops, then after 10 cycles, the one appears here, and you just clear the flip-flop. Then you will have exactly this the solution. Now you can actually run this design, which is implemented here in simulation, and compare it against this design in simulation, and it will be the same. That's the idea. So in this case, you see that would be the definition. That would be the entity. Yeah, the clock is input, the I is input, the O is output. So this is actually this box here. And now here, this process is sensitive to a clock. This means whenever there's a clock here, see, whenever there's a clock, we will also learn how to do this. Whenever there's a clock, then we just load the shift register with the I. Whatever I is input, we load this, okay? And then, at the same time, we also shift by 1 position, okay? And this is the loading and shifting. And then we're asking if the output of the register, and we load this here, see? This is for example, 9, and this is index 0, and we shift in this direction. So this means if the output of 0 is 1, this output 1 is here, then we just clear the output, else we just, but if this is 1, then is then it's Z, and then you see that's what we describe, and then we will get this function. You see, that's a difference. Okay, this means that structure and behavior you describe for simulation is usually very simple, very simple. You know, it's very simple. You can use these statements like wait and wait down a little bit and maybe wait until this. But if you need to synthesize now, you have to understand the real function, because now we need really describe the function which is synthesizable. So in this case, we have to deal with adder, counter, flip-flops, RAMs, and so on. So you need some kind of understanding of the real hardware. Okay. So again, this was just the overview. You know, synthesizable, non-synthesizable. So now more the information, let's say, designing with VHDL. This means what are the steps? We do a few minutes, so we can actually spend time here to have at least the first idea. So whenever we design our circuits, we have to deal with so-called design units. Okay. So what is design unit? We do have actually two important design units. There are actually 4 of them, but we will talk a little about configuration and package. We will talk in the second part. But today we will talk about 2 very important units. One is the entity and one is the architecture. So these are the units which describes actually your design. So the entity describes a box. So it describes a component called ABC, whatever the name is, and describe the name of the inputs and the name of the outputs. Nothing else, just the view from the outside world. The architecture describes what is internally. Okay, so it means entity and architecture always belong together. Entity is, that's how it looks like from the outside view, and architecture, this is what's inside. Okay, always belongs together. So, for example, I would like to describe this block called register. So first, I define the entity. So this is usually a text file. Entity. Now the name is. Port means the blue are the keywords. Port, this means is the port called DIN. What type? What is it? This is an input. Oh, okay. And what type is it? Remember, we have always, no exception, defined the type. In this case, the type is a vector, which is 8-bit wide. Okay, it's an 8-bit. Now, next port. Oh, it's the out. Okay, the out. This is an output. Okay, output. What is it, the type? It's also an 8-bit vector. Okay. Now, next port. This is a clock. Is an input. This is a single. Standard logic is easiest way to imagine this. It's actually a digital signal. Okay, it's a standard logic called standard logic. It's a 1. No vector, just 1 signal. Yeah, because it's a clock. That's it. No more information needed. Entity simply tells you this is how the block looks like from the outside world. That's entity. So, and then the next block, it's architecture. Just here, the next block, architecture with a name. You need always a name. Usually you call it XX or behave or something like this. And of registers. You see, that's a relationship. This is the architecture of the entity register bit. This is the name, is it? This is a reference. This is the internal structure, internal behavior description of the entity defined here. Now, the name is the link register. Now, you see, and we can almost immediately read the behavior. Process means whenever process, and that's called sensitivity list here, we will also talk about this, means whenever there's a clock is changing, the clock is something like this. So the clock may be changed rising or change falling. It's just the clock. Yeah. Because the clock is, the clock can do everything. Clock looks like this. And now you're asking here, oh, if this is a rising edge, you're just interested in the rising edge. It's the rising edge. This would be the falling edge. But we are just interested in the rising edge. If the rising edge, then please go ahead and take the input day in and transfer it to the out. So this means, what is it? This is nothing else as a 8-bit wide flip-flop. This is a flip-flop which is clocked with the rising edge of a clock, and whenever this happened, then it transferred. If no clock, no transfer will take place. If you would like to use the falling edge, then you actually can say falling edge. Then you will have the falling edge. Okay, so that's what we do. This means this is these are the basic elements, or not the element, design units used in our FPGA VHDL design. Okay, so this means entity describe how the block looks from the outside world, and the architecture defines what is inside. And this belongs together, always together. And now you see already, now you see the design units as entity and architecture. Yes, you see also the typing, the types, let's say, the types idea from VHDL. Whenever you define signals, input, output, you have always to use the type definition. Always, there's no exception. Always, and only objects which have the same type, like here, might be, assigned to each other. This means, you see, that the in has the type standard logic vector, and the out is also the type standard logic vector. So this is okay. If you use a different types, you will get an error. There are some methods, like in C, you can do the casting. You can translate the type from 1 to the type 2, but you have to do it manually. Okay, automatically it will not happen automatically. Okay, so this means, and this is again, that's maybe the most important information here. We do have actually two types when we using VHDL. Two types of our design. We can do structural. So this means the structural looks like this. We could use primitive components like gates or flip-flops, connect somehow, or we can use hierarchic elements that's to build something. And this is called structure, because there's no behavior at all. We just place this element, and this element, and connect it somehow. It's called structure. Okay. Behavioral is something different. Behavior is something like this. You just have here some inputs and some outputs, and now you write text. Just describe the behavior. What should be done with the inputs in order to generate outputs? Okay, that's a big difference. This is called structural. This is called behavior. Usually, we do have a mix of both. That's what we do. Usually, this means how does a typical FPGA design looks like? It looks like this. This is your FPGA. Now, maybe your FPGA is connected to an external microcontroller somehow. Okay. Then inside your FPGA, now you would have maybe a block which contains an interface. This block might is connected to I don't know, to memory, to RAM, and then this interface might be connected to some kind of a control structure, and with this control structure maybe controls the RAM or whatever. Okay, so it means that first you draw the hierarchy. So these are hierarchical blocks, and then But the internal operation, this now is described as behavior. That's what we usually do. This means structural is today doesn't really refer to using primitive components. Nobody's doing this anymore. No. Structure usually refers to producing hierarchical blocks. This is just to do the block diagram. That's maybe the top level. And it's very easy to read. It's very easy to maintain and easy to understand. But now, if you go inside this block, now, of course, you benefit from the behavior description style, and now you write the behavior of this block. And this is what really happens. So, but you see, that's we're finished for today. Also, sorry, I'm 5 minutes too late. So this means we will continue next in the next session. But today, I just gave you an overview and some very simple, easy instructions. How can we use VHDL? Thank you very much for your attention. And if you like, we will meet again for the next part, second part in the in our next session, which will take place in May. Okay, and thank you very much and have a nice time and goodbye.